Hello guys, so this is the second video for motion in 2 dimensions. What you're seeing right now in there is the ski problem. You are coming down the slope and then you are leaving with some speed and then you are gonna end up landing at certain point here. So the problem asks you, what's the distance where you land from the slope on this slanted line, right? Realistically speaking, normally you have bumps and stuff, but you can have some sort of a slope given by an angle there. So the problem is very easy if you realize what I was doing at the end of the first video. You see, respect to the horizontal, the velocity or the speed, that the ski has when it leaves the slope in the jump is horizontal, right? Horizontal. There is no vertical initial speed. Now we know that gravity is always pointing downwards at negative 9.8. So there are three ways of doing it. One is the one that you have in the slides. But that will be overly complicated, especially if you don't remember the equation for D, which we did last class. So let's see how will you do this in like some sort of setting. And there are other ways of doing this, by the way. You can apply a lot of trigonometry. For example, if we look at the problem from this perspective, right? You can tell that the speed can be broken into these two components. You can break the speed like this and like this using this angle. But there is a problem if I do that. This speed is not constant anymore because gravity, even though it's pointing downwards, gravity, if we break into components, right? Let's actually do it here. We can break gravity going this way and this way. Gravity can affect on this direction and on this direction. Because this angle here is also 35. That's easily proven using trig. You can put your vector, you have another one here, you have 35 degrees here, and gravity is going all the way here. So this is 90 degrees. I want gravity that is perpendicular to this. 35, 65, 35. So this angle is 35. So I can break gravity like this and like this, of course. So gravity is making the object accelerate. So that will make it very complicated. Let's make this more simple, way more simple. How? We're going to use free fall projectile motion. So let's actually leave gravity going down. And we can draw this dotted line, dashed line, and we have a free fall projectile motion where x is your range and y is your height that you don't know, but you write the equations for those. There is no vertical initial speed. So on x, you only have 20, and then horizontally, gravity doesn't affect. Gravity only affects vertically and in the angles like this, like I showed you. But there is never gravity acting like this horizontally, right? So x is just 25 times the flying time t, right? And then the height, y, is the initial speed times time, but there is no initial speed, right? The initial vertical speed is 0. The guy is just living with a horizontal. So this will be a free fall of 1/2 gravity the flying time square, the time in the air. We need those two equations in there. Let's look at this triangle. 90 degrees, 35. What's the angle here? This line is parallel to this line. Alternate interiors gives me this to 35. So what's the relation between y and x? From trigonometry, y divided by x equals to tangent of 35. Now, I will use my equations for y and x. Y is 1/2 9.80 squared and x is 25. That's equal to tangent of 35. Now I will solve the equations here. Time with this time cancels. You get 9.8 divided by 50 equals to tangent of 35. 9.8 times time, sorry. Let's make it more clear here. 9.8 multiplied by time divided by 50 equals to tangent of 35. If you solve the equation for time, you get 3.57 seconds. 3.6 almost, right? Seconds. And that's it, guys. You replace time here and here, and you will get the values of x and y. I can erase this now. And then I will put here x equals to 25 times 3.57. And I use now my calculator. $89.3 meters. I believe that's the answer you have in the slides. And the position and the height that he falls 62.4 meters. 62.4. So there you are. If you have x and y, you can apply Pythagoras and find the value of d, which is approximately 120 something, I believe. 119. All right. There are other things that you can find. I mean, I found information that you were not being asked, the time it took to land on that point. As you can see, this procedure is way more simple. All right. So that's the problem that you have in the slides with the ski. Now I'm going to do a problem that is similar to the web assignment. So you want to watch this or maybe even rewatch it because it's been recorded anyway, right? So that's the advantage. Even though I'm erasing all this, you can always go back and take a look, right? Trigonometry is very important. We are going to be doing another problem with now throwing an object from the top of a building. So now I'm going to give you, so you have here the ground. And then you have here a building. I'm gonna say that this building has some height of 100 meters. All right, just make it like that. And then you are gonna have a projectile or a ball or whatever, but you are not gonna just be going to launch it like this. You are going to launch this ball or projectile at some given angle. I'm gonna say this angle is 37 degrees. So the ball, obviously, is first going to go up and then gonna come down like that. It's a very interesting problem. Okay. So obviously, I'm going to ask you to find the range, but then I also want you to find the maximum height it reaches. And also can ask you the flying time. This is a problem where the time to go up is not the same as the time to go down. It's not. Because of the symmetry. The symmetry only lasts till around here. But then, looks better, right? But around here. But then it keeps going down. So the time to go up is not the same. It's not the same as the time to go down. Because the time to go down requires all this height. The time to go up is only this. So in fact, I'm going to call this H. And you know obviously that this is 100. So H plus 100 is Y. That's okay. The only thing that we always have is gravity going down. So let's start. Okay, I didn't give you the speed, so let's say this is 30 meters per second. Okay. The first step will be to break the speed into components. This will be 30 cosine, 30 sine. So 30, the cosine of 37 is 4 over 5. We did that last class. So this is 24 meters per second. And this is 30 sine of 37, which is 3 over 5, 18. So this gives me 18 meters per second. So it goes up, certain height, and then it goes all the way down till here. So I want to find H. How much it goes up? We know that at the maximum height, H, the final speed on Y is 0. On Y, not on X. On X keeps flying, right? So I'm going to use this. Again. Maybe this, hopefully. Yeah, this one. Be final on Y, be initial on Y, plus or minus gravity, the time, let's put the time to go up. I also want to find that. Oh, by the way, I don't have time. So remember, if I don't have time, what equation do I use? This one. Be final on Y squared equals the initial on Y squared plus or minus 2 gravity H. The final on Y is 0. The initial on Y is 18. So 0 squared equals to 18 squared minus, because gravity is going down, 2 times 9.8 times H max. That's how I find H max, by the way. 19.6 equals to 324, 19.6 H, right? equals to 18 squared, 324. So the value of h would be that divided by that, 324 divided by 19.6. I get 16.5. Yep. 16.5 meters. So it went up all that. So y, I can put here, y equals to 100 plus 16.5. That gives me 116.5 meters. That's how much it will go down. So I already found the maximum height. However, to find x, I need to know the time to go up and the time to go down. So I'm going to erase that. I'm going to use this equation to find the time to go up. So I can use this now. 0 equals to 18 minus 9.8 times the time to go up. The time to go up is equal to 18 over 19.8, or 9.8, sorry, 1.84 seconds. And I will leave this aside because there is no symmetry. So now I have y, and I know that the object is going to fall up until here. So it's going to have now a free fall. Free fall, and I can put here where y is equal to 116.5 meters. That's how much is going to fall. I can find how long it takes to do that. Because it's a free fall means that there's no initial speed. So 116.5 is equal to 1/2 gravity times the time to go down squared. Now that's how I find the time to go down. Times 2 square root 4.87. It takes more time to go down. That makes sense. 4.9 seconds. I found the time to go down. I have the time to go up. So now I can find x. How, will you ask? X, guys, here, x is the horizontal speed times the total time. The total time is the time to go down plus the time to go up. And that's how I find x. So let's do that where? Let's erase this now. And let's put it here. The time is equal to the time to go up plus the time to go down. 1.84 plus 1 plus 4.9 is 17, 4, 5, 6, 6.74 seconds. So the value of x is 24 times 6.74. There's something that it's very different to the example in the book. I don't use any quadratics. I don't use any of those complicated equations. I just use physics. 155.28, 155.3. It's up to you guys what method you want to use. You can use the method I showed you today, or you can use a method from the book. I feel like this method allows you to see it more thoroughly and more clearly what's going on. You first break it to components, you find the time to go up, you find the height, it goes up, and you add it to the height of the building or whatever it is, you find the total height and you use the total height to find the time to go down. Time to go up plus time to go down is the total time the ball or the projectile is in the air. Multiply by the horizontal speed, that gives you the range. It's all physics, all clear. That's another example there. So we did two very nice examples today. All right. I want to finish this video just showing you guys constant circular motion. We're going into motion on 3 dimensions. And then we can do some examples from WebAssign on the next video. All right. I'm actually recording this video the week before we start classes. So I'm basically covering the first 4 to 5 weeks. 4 weeks actually. So what I will do is I will be doing Newton's laws. While in the meantime, I will try to meet with you guys online so we can discuss the syllabus. We can discuss, you know, the expectations, the quizzes, and all that. All right, so just as an introduction for the constant circular motion, I'm going to make it very simple. We call it constant because there is just one acceleration. And you're probably thinking, how come there is an acceleration? Well, what did we learn last time? We learned that in order to have acceleration, the speed has to change. Well, the velocity has to change, right? But also the direction has to change. You can have a particle moving like this. You can have on this point moving like this. It can be the same velocity, by the way. But because the velocity is changing directions, we say that there is a acceleration due to the circular motion. This acceleration always points towards the center. We call it the centripetal acceleration. And we label it like another vector AC. And also we know that this has a radius of magnitude R, and that's your constant circular motion. What are the properties of a circular motion, of a constant circular motion? A constant circular motion has period, has constant speed, period, and frequency. The period is the time the particle takes to go one revolution. What is one revolution? One revolution is equal to 2 pi radians, strict. So this is the label for period, capital T. The period is equal to the distance traveled by what? A speed, but it's not v though. V is what we call the linear speed, straight or up. In circular motion, we call it an angular speed, W. W is the angular speed, or angular frequency, by the way. What are the units? Period is in seconds. 2 pi is in radians. The angular speed is in radians per second. All right. Now, let's find the analogy between circular and straight lines. So, what is a circumference? Okay, if we're giving a circle, every circle, you know, has a given circumference. The circumference of a circle is equal to, so I'm gonna write it here, the circumference of a circle is equal to 2 pi r. This is the linear, the length of a circle. So I can also define the period as the total length of the circle. Now I can use V. Ooh, ha. So, and what? What's omega? Omega is equal to the linear speed divided by the radius. There you are. That's how you relate those free variables. What is the centripetal acceleration? The one that was showing you there. So the centripetal acceleration is defined as, so the centripetal acceleration is defined as the velocity squared divided by the radius. That's in meters per second squared, by the way. So even though you're in a constant circular motion, means because the speed is not changing, you have a centripetal acceleration. We will later study circular motion with other accelerations, right? Angular and tangential. For now, we are just looking at centripetal. Now, how can we use vectors in this case? Or positions? In the case of a circular motion, if I take this as the origin, I can draw a vector R. The vector position will be this. Now, we know that if a particle starts from here, it's going to move an angle theta. Okay, so let's use this again, and let's use our definitions of constant speed. For constant speed, we know that the displacement is equal to the speed, velocity times time, sorry. The angular displacement in the circular motion, we call it the angular displacement, is defined as delta theta. That's equal to omega times delta t. That's the analogy there. So we know what this angle theta is in, and we can tell this is the x-axis, this is the y-axis. We can tell that position vector in terms of x and y, right? The position vector r is x on the I direction, the unit vector I, plus y on the j. Now what's x and y? X is this, so I can build a triangle and I can break this vector into components, r cosine, r sine. So I can have a vector, right? That vector can be written, let's put it here. If I break vector into components, it will be the magnitude of r cosine theta I plus the magnitude of r sine theta j. But what was theta? Omega t. So the magnitude of the vector r cosine of omega t plus the magnitude of r sine omega t j. That's the vector position Those are the components, basically. Right, there it is. So let's not forget period. And what's frequency, by the way? Frequency F is equal to the inverse of period. The unit for frequency is 1/seconds or hertz. All right, so we have this definition. And let's take a look at these slides now to see what's left on this chapter. So we did this. We've done that. We did this. We did this. I think you guys can take a look at this. We found this. Okay, so here, this is very interesting because now on the last slide for circular motion, they do show you the tangential acceleration here. So the tangential acceleration is just the acceleration that is on the same direction as the velocity. As you have seen already, the velocity is always drawn tangent to the circumference. So the velocity and the centripetal acceleration make an angle of 90 degrees. But there is an acceleration that makes this V change. When we're not talking about constant or uniform circular motion, this V changes. So you can use that and find the tangential. We will do more of that later. This is just for you guys to see. And by the way, yes, the tangential acceleration is the first derivative of velocity with respect of time. The centripetal acceleration doesn't have a calculus definition. All right, that's very important. There are two different accelerations. And of course, the radial acceleration and the tangential acceleration, they give you the acceleration, right? The total acceleration. But don't get confused, guys. When you find the derivative of the velocity, you are getting the tangential acceleration. That's something that it can take some time to get used to, but now we are, that's why it's called in 3 dimensions. All right. A particle moves along a path and its speed increases with time. In which case is so that's interesting. In which case the acceleration and velocity vectors are perpendicular everywhere along the path. They are never. Only if the speed is constant and it changes direction, that is when the acceleration and the velocity could be perpendicular. But in any other case, no. All right, you can also see that in here. This acceleration is never perpendicular to the velocity, which is tangential here. That's because there is already tangential acceleration. All right. So that's what we answer. Okay, so here they give you, so we can probably do this later. I mean, what do they give you? A car list, stop sign, and they give you the acceleration that and the radius of the loop. At the moment, the car is on the top of the rise with this radius. Its velocity vector is 6 meters per second. What are the direction and total acceleration vector for the, okay. So this one is not that difficult though. This one is just following what you had in the previous slide. You have the tangential acceleration, you will have the radius acceleration. So you can find the total. So actually, let's show you this so we can use the equations for centripetal and acceleration. All right. So we can use this as well. Pretty much what they are telling you is that you have a particle that is moving on a circular motion, sort of, and you have 6 meters per second, but you also have an acceleration of 0.3. And the radius is 500. So the centripetal acceleration always goes toward the center. So let's find this, but well, I can just say that this is the centripetal acceleration. And then what I just drew here, this is the total acceleration. And then they want to find this angle theta, which is that the tangent of theta is AR, or A centripetal, over A tangential. I have A tangential. How do I find A centripetal? B squared divided by R. I believe in the web assigned there is a problem like this as well. I will discuss about it on the next video. I just want to do this extra for you guys. 0.072. So radial vector there. Total is this square .3 square. So the total acceleration is 0.005184. 0.31. It doesn't get affected too much by that. Still. And then theta AC over AT and the arctangent is 13.4. Well, I got the answer. 13.4. They put negative in the answer because it's below the horizontal, but you get it, right? All right, guys. We will do more problems on circular motion later, but the definition of period, frequency, that's also important. And I hope that this was clear, and I will see you guys on the next video.